D.2, exercise questions, set number 3. In this one, I will give you a few more questions because we have a little more time near the end of the module 1 in order to complete the remaining part. So I used the remaining 2 videos, one for the exercise questions, another for project 1. All right, so let's look at our first question today. No algorithm can be optimal because one can always improve a given algorithm. If you have not learned the materials so far, it is very likely you may feel the statement is correct, right? Because by the intuition, so many people answer this question just by their intuition. But your intuition could be wrong. Actually, many times your intuitions are wrong because you do not have sufficient knowledge. After you have the knowledge, you need to change your intuition. Okay? Now, here, why it is wrong? Very simple. Do you remember we just finished that problem number 3. Find the minimum. Okay? Then we use very convincing arguments to show it is optimal. Nobody can improve it, no matter how smart that person is. He or she can never improve our algorithm. Okay? So we get a counterexample. Yeah. So we answer by this example as the counter example. Okay? That's the knowledge you need to answer this question. If you don't have this piece of knowledge, it may not be easy to answer this question just by intuition. All right? Okay, yeah. Next question. Nobody can show that certain algorithm is optimal because you cannot exhaust all the algorithm for solving a particular problem. Think about this. This is a question not very easy to answer for most of the students. Okay? The reason is, here the reason, okay? This because part is correct. Okay? Because part is correct. Yeah, no problem. Yes. You cannot exhaust, nobody can exhaust all the algorithms for solving a particular problem. Nobody can exhaust. Okay? So the because part is correct, but cannot conclude the main statement. Nobody can show that certain algorithm is optimal. We showed, right? We showed. Problem number 3. Yeah. So we refer to that problem number 3 again. We showed. Okay? Yeah. But here, there is something a little deep I may need to explain. Yeah. So why the because clause is correct? So yeah, nobody can exhaust, but we can still show certain algorithm is optimal. In other words, we can show certain algorithm is optimal without exhausting all the algorithms for this particular problem. Why we can do that? Yes, we can do it. Yeah. So here, let me write it. Yeah. So we can do it. So you know what kind of thing. So I do not write long sentence. So we can do it without exhausting. Yeah, all right. H. All the algorithm all right, yeah. So yeah, save some words. We can do it without exhausting all the algorithms. Why? Because we can find some common property or properties for all those algorithms. That's the main reason. We find common properties even if they are unknown. Right? Yeah. Even for those unknown algorithms, we can still find common properties. That's possible. That's possible. We can do it. Right? Elimination, remember, in our find the minimum question, problem number 3, insight. Remember the insight, that elimination insight. That's the common property for all the algorithms without specifying the details of those algorithms. That's the power. Okay, that's the power. The common properties, finding the common properties, that's possible. Yeah, so later we will use this method another time. Later we have other chances. We will use this way to get a very good results. All right, yeah. So let me go to the next question. This one. Given a polynomial with the form, yeah, so the formula here, but you can see A0, A1, A2, A3, A4, these coefficients, you can choose different values for them. All right. Is it possible that one can find a special case? Yeah. So here we are not look at the general case. Yeah. Because for the general case, then we should use the Horner's rule. General case, we should use the Horner's rule. For the special case, then we can do better than the Horner's rule. Because special, yeah, here, such that the number of multiplications to evaluate the polynomial is less than 4. Okay? We know using Horner's rule, we get 4. Yeah. The answer equals 4. Okay? Then you can choose special coefficients for these numbers. If you choose special coefficients, can you do better than 4 multiplications? Yes, the answer is 2. Yeah. Here, let me give you some example, interesting example. Yeah, we will see that. Okay, all right. A equals 1. 1, A1, 4, A2, 6, A3, 4, A4, 1. Okay? When you see these coefficients, these numbers, can you connect to something interesting? Can you connect to something interesting? These numbers, Pascal triangle. Have you heard of that Pascal triangle? Have you heard of that Pascal triangle? These numbers correspond to that Pascal triangle. Okay? Yeah, I hope probably you do some web search, find that Pascal triangle. All right, based on that, this polynomial can be written as 1 plus x to the fourth. Okay, equals that polynomial. All right, when you have that, let's look at if we can use fewer than 4 multiplications to find the answer. Yes? Because you calculate 1 plus x first. You already, you don't need a multiplication, right? 1 plus x. After that, to get 1 plus x to the fourth power, you just need you just need 3 multiplications, right? Not 4. Already you save 1, you can do better. But there is another way you can do even better. Okay, all right. So let me show you the smart way to do even better. Okay, 1 plus x, you take square first, 1 multiplication, right? 1 plus x squared. Then when you get to 1 plus x to the fourth, you multiply square by itself. Okay, here you do not need to do another multiplication because you already have this value from, the previous calculation. You just use it. You just copy its value. Why you need to do multiplication another time? You can save 1. So then this multiplication, another one. 1 plus 1, sorry. Yeah, too sensitive. 1 plus 1 equals 2. Okay? So here you can see you just need 2 multiplications. Better, right? Much better than 4 multiplications. Yeah. All right, so here for the question, for the answer, it is possible. Yes, it is possible because we can do it. Yeah, so that's very interesting. Right? All right, so let me bring back this old question at EX2, Q1.3. This one, remember at that time I talked about the coefficient part, no pattern, right? No specific pattern. Then we have to use the Horner's rule. No specific pattern, Horner's rule, so the answer is the highest degree number. But I said if there is some special pattern, that number can be reduced. Now using this question, you can see this is the pattern, okay? This is the pattern. Using this special pattern, you can see the number can be greatly reduced. How about that? Okay, so that's pretty interesting. Yeah. All right, so that is the third question today. All right, this one, the fourth one. Yeah. For this question, yeah, what is the minimum number of multiplications we can get to compute the expression a to the 9th? All right, a times x to the 9th power. Yeah, a times, so 1 multiplication here, right? 1, yeah. Then the remaining, to calculate x to the 9th power, how many multiplications do you need? Think about it. Okay. Is it 8? Yeah. Is it 8? Yeah, because the degree number minus 1. Yeah. 1 by 1, multiplied in that way. Yeah. But that's not the best way. Why? If you look at our previous example, we have a special technique. So remember, 1 plus x, when we get to square, we double. We double the exponent, one multiplication. Then we do another square. We square this number another time to the fourth, another multiplication. Can we use this technique to solve this question? Yeah, this method we called repeated squaring. Repeated squaring technique. Very interesting. Repeated squaring technique. Let's try that. Repeated squaring technique. Okay, all right. X times x equals x squared. So one multiplication. Okay, all right. The second, x squared times x squared, because we already have the value. We just use this value multiply itself, equals x to the fourth. Multiplication number 2. Then x to the fourth multiply itself. We already have its value. Yeah, we just square it. Yeah, x to the 8th. The 3 multiplications, right? Accumulatively 3 multiplication. The last one, x to the 9th, x times x to the 8th, x to the 9th. 4 multiplications, all right? Plus this one, so the total, using this technique, our answer equals 5. 1 plus 4, 5. Better than that 1 plus 8, 9, right? 9. All the way 9. This repeated squaring way, 5. Is it better? Is it interesting? Yeah. Very good. But not done yet, because there is another interesting technique we can use to improve the result. So let me show you the last example, last case. Still this example, but the last round solution. Yeah. All right, so this time, all right, so a times x to the 9th, this is 1. We cannot save this one, so we still keep this multiplication, but we work on the x to the 9th part. We hope we can do better than that repeated squaring technique. Repeated squaring technique, already pretty good, but we want to do better than that. Yeah, based on the structure we have here. Yeah, let's take a look. X to the 9th, we can write it as x cubed times x cubed times x cubed. All right. If you can find x cubed, then you just need 2 more multiplication, okay, to get the result. 2 more multiplications. Okay? Because you already have x cubed, you just use the same value, you know, as 3 operands to get the answer. 3 operands, cube operation, okay? Yeah, 3, yeah. All right, but how many multiplications do we need to calculate x cubed? Okay, 1 here, 1 here, so 2, okay? 2 to get x cubed, then 2 more to get x to the 9th, total 4 times. All right? Oh, yeah, total 4 times. Yeah, 1 plus 4, answer 5. Yeah, same answer, right? Yeah, same as before, but in different way. Okay? Yeah, same as before, but in different way. Okay? Yeah. Later in the future, you will see when the exponent number larger, you will see we can do better. So this one we call repeated cubing. Okay, that's squaring. The previous one, repeated respond pretty slow. Repeated cubing. How about that? Repeated cubing technique. Yeah. All right. So you can see with repeated squaring, with repeated cubing, we can make monomial evaluation. Yeah. So this whole thing we can call it yeah. This is a monomial. Okay. We do not include the A part. This whole thing we call the monomial. We can make the monomial evaluation much faster. Okay. All right. So let me finish the video D.2 right here. Yeah.